So thermochemistry and kinetics for our week 7 lecture, and that will be the heat is involved in this content, and the reaction rate, how fast or slow the reaction will happen, those will be involved in this reaction. So for this topic for discussion. Now let's go to see that what is our my computer hang. Okay, so let's see our objectives. What we want to learn from here is describe the changes of energy that occur during chemical reaction using energy profile diagram and del H notation. So there are two things that we will be learning, that how to draw an energy profile diagram for a reaction that is happening, and what does that energy profile information, what the information the energy profile is giving us by the mean of del H. H is actually enthalpy, it's called enthalpy. Enthalpy in a very simple way to put is the heat of a reaction, all right? Enthalpy is the heat of reaction. And when there is a del sign in front of it, right? When there is a del sign in front of H, that means the difference. This is the difference of heat, difference from reactant to product. How much the heat is different from reactant go to the product. So that is why del is used, the delta sign is used. Okay, and later on, when we move further deep into this discussion today, we will see the collision theory. We will learn about the collision theory, or why, what is happening when the reaction occurs, what is happening in between in a molecular state, and how this rate will be dependent on the concentration, the particle size, the temperature of the reaction or the environment we are having, and some more, that is the foreign thing that, not a reactant thing, but it is a catalyst. Catalyst is the foreign thing to the reaction, but it has a very, very significant, very high impact on the reaction rate. So, energy and chemical reactions, how are these two related to each other? When the chemical reaction occurs, it happens due to the collision, right? The atoms, the molecules and ions, they collide each other to produce a reaction and to produce a product, all right? And then during the chemical reaction, the bonds form, broken, and then it formed again, right? And during this bond formation, breaking and formation, there lies the main thing of a reaction is happening, that is the product. And due to this bond breaking and bond forming, there will be changes in energy of the new product, right? Like A and B are reacting. Like here I write A and B are reacting, right? This is the most given example for a chemical reaction, I think. A and B are reacting, right? And then C is produced. A and B are reacting and C produced, right? So this is a arrow mark. So C is produced. So that means the C is somehow contain A and B both, all right? A and B both in the C. So the formation of bond that A and B has in this C, and the A and B, the bond they had originally, that is the heat for formation of C, and the heat they had originally, that is the difference between them, is the del H, and this is the enthalpy of the reaction that is occurring for a system. When the reaction occurs, there are two possibilities for the heat changes. All right, heat, either the reaction can produce heat, or the reaction needs heat to be provided with. That means either the reaction can give us heat, that is the stove, the gas, right? We cook our meal, food by using our gas stove. So that is the reaction is happening. It is giving us energy, heat. And the another thing is also possible, that we have to provide some heat for the reaction to occur. So when it is giving us heat, the reaction is giving us or generating or producing heat, it is the exothermic reaction. The exothermic, that means exiting heat. All right. And when the reaction requires heat to be provided to it, that means it takes heat from the environment, is an endothermic reaction. These two terms are quite confusing. Sometimes students always have problem to remember, but you have to, these two are important. You must remember this thing. Exothermic is exiting the heat. That means the reaction is producing heat, and endothermic, the reaction requires us to produce, give heat to it. Okay, so, and that is why the del H is less than 0, and for endothermic, del H is more than 0. And you will be surprised that exothermic, that is giving us heat, we will show it in negative sign. All right, negative sign. And endothermic, we will express this reaction with positive sign. So these two things are again confusing, but just remember, exothermic will produce heat, will give us heat. Or if you want to remember in that way, that if we turn on the stove, right, the stove, the gas stove, we have the burner, and it will give us heat, that is the exothermic reaction. All right, and in reaction, when we write it for the reaction, we will show it in negative sign. We will show it later on, we will come to that. For endothermic, this is just the opposite thing. If you want to know that if we dissolve some salt in water, the water temperature becomes, the glass, if we touch the glass, and if we put some more salt in the water, significant amount of salt in the water and dissolve it, you touch the glass will feel a bit colder, okay, a bit cooler than the previous, what we had with the water, the temperature. So that means the salt, to dissolve the salt, the salt to be dissolved, it took heat from the water, and that is why it becomes colder. So that is the endothermic reaction. This is the two different example you can remember to remember it. For one equation, actually, this is already given, and you know this thing already, but in the class we show it to the student when he's face to face. So the question says that which statement are correct for all exothermic reaction? The enthalpy of the product is less than the enthalpy of the reactant. Okay, this is true, as it is showing, and the sign of del H is negative, what is I just out. But the reaction is rapid at room temperature. The reaction is rapid or slow at room temperature or high temperature. This is something else. This is the rate of reaction or kinetics of the reaction that we will come later on. It does not necessarily for endothermic or exothermic. There are other factors the rate of the reaction. So what will happen is the enthalpy of the product is less than the enthalpy of the reactant. Here we see the previous slide, the exothermic, you see the reactant energy is higher because the energy is going this way up. That means here if it is 1, it should be more than 1, maybe 5, let's say, okay? So this is y-axis is going up this way. So the reactant energy or enthalpy is more than the product. And the difference, since the difference is here, the product has less energy than the reactant, it is the exothermic. That means the product has less enthalpy than the reactant. And the just opposite thing is true for endothermic, higher energy than the reactant. Let's go to menti.com. I have prepared one. Delete it. Easy. Okay, so any question? So what is enthalpy? And so for exo reaction, the reaction is slow if it's not rapid. What is enthalpy? Enthalpy for Claude, if I can pronounce your name correctly. So for enthalpy is the heat of reaction, all right? How much of the heat the reaction will involve, whether it produces or it takes, or the energy of the product or reactant altogether is enthalpy, all right? And enthalpy and entropy, that's very good. What do you know about entropy? Okay, before that I go to Rizvi. So for exo reaction, the reaction is slow. Exothermic. No, that's what I think I just mentioned, that for reaction rate, we have to consider some other factors, all right? Other factors we should consider for reaction rate. So this is not only exothermic will be faster or endothermic will be faster. It is not. There are other things that will be involved, and we will go there. It's not yet. Jonathan, what is the relation between enthalpy and entropy? Entropy is the disorder of the system, all right? This is the most simplest way I can explain. There is no definition for entropy, but this is the most simplest way I can put it, that it is a disorder. So when the enthalpy is increased, the disorder will be increased in a simple way, but there are some other consideration that is, we don't want to discuss it here. We will learn more when you go for higher studies, hopefully. Okay, so let's go to the menti.com. And I give you the passcode. Please do it faster because I have to finish it with 2 hours, already 1.5 hour, half an hour gone. The passcode is 5379. Hold on. 5379 4949. This is the passcode. Please go and faster, okay? Don't have much time. We have to finish it. The count, you have only 1 minute to do it. Faster, faster. Oh, you don't see Menti, yeah? But you go to the Menti, the countdown started already, okay? Faster, faster, faster. "20 seconds." Yeah, 20 seconds now. Okay, voting finish. So there is quite good distribution. 16 here, 5 here, 5 here. There is a very okay, 5, 5, 10, and 16 times plus 10 is 26. So what are the other students that you guys are doing? Why don't you just click it? It's too difficult for you. Okay. Anyway, those who give their 16 of you, the pink color, congratulations, you got it right, because the reaction occurs because they want to form a new bond for a favorable compound, all right? They want to form, that's just now, I think in the third slide, we talk about it. The reaction, those who give this 5, thank you very much. At least you tried, but it is not a correct answer because the concentration, the reactant different concentration, does not necessarily mean that it will have a reaction. Those components have the different concentration, they must be able to form a bond, all right? If they do not form a bond, then does not matter what concentration you put them, they will never do the reaction. And those other 5 who click here, the high temperature forces to occur, it is not necessarily true that I just discussed, I think, few seconds ago, that high temperature will not always favor the reaction. Sometimes we have to have low temperature so that the reaction will be favored. And we will talk about it in a bit. Okay, so let's go to our lecture slide as well. So the equation, is there any question? What is a reaction? I think it's reaction. Reaction load, what does it mean? Any reaction, for any reaction, it was general reaction, okay? All right, so let's go to these slides again. Okay, so thermochemical equations, what is happening, how it is happening, that is our consideration today. That magnesium, right? This is magnesium is the first group element from the periodic table. You will see that it is just after potassium is magnesium is there, sodium, potassium, magnesium, potassium, sodium, magnesium is there. If it reacts with water, is violently reacts with water and produces magnesium hydroxide, all right, and hydrogen gas. And this technique or technology, should you call, can be used for this type of emergency situation when the wartime or you go for campaign or something like that. This type, when you don't have the time for lit up a stove or you don't have a stove, you can warm your meal, just put some water in the bag. It will produce a lot of heat, and that's how it will make the food warm, and then you can eat. And this reaction, it happens in this way. So magnesium and water produces magnesium hydroxide, hydrogen gas, and this is the 353 kilojoule per mole. All right, 353 kilojoule per mole of heat it produces. It's quite much of heat, and this is an exothermic reaction. See, it is exothermic reaction. It is producing the heat. That means if I put water with this and it is in a beaker, let's say it is in a beaker, then this beaker will be very hot. That means the reaction or the system is producing heat, and the amount of produced heat is 353 kilojoule per mole. But you see here we put negative sign. Don't be confused, but this negative sign means this is exothermic. It is producing heat. Okay, the heat is being produced from the reaction, but it is negative sign. This negative sign, actually you can remember in this way, that this is also a reactant. Okay, it's also a reactant, so it will go in this way, and since it is negative 353 on this side, so it will be positive on this side. But don't have to be confused. Just remember that if it is negative sign, that is the exothermic reaction and it produces heat. All right, so if we produce an energy diagram for this reaction, all right, exact reaction energy diagram we want to produce, we will see that magnesium was here, all right, and then here was the water molecule. Magnesium is solid, all right, this is solid magnesium, yes, and water in liquid form. It is the energy of this reactant was here. Let's say it is X. The energy is X. So when I added water to this magnesium, what will happen is there will be a product, magnesium hydroxide and water, hydrogen gas. And since this reaction is producing heat, it must be exothermic, and for exothermic reaction, the enthalpy of product is less than the enthalpy of the reactant that we already have discussed in the previous slide. So the reactant must be at the lower end of the energy diagram, all right? The reactant must be at the lower end of the energy diagram. Okay, so here it is. The product is here, that is at the lower end, and the reaction will go in a way that it has to overcome the hurdle. There are some hurdle that this reactant, both reactant, magnesium and water, they will mix together, but still they have to cross through a go there to the product side. And what is that hurdle? That hurdle is called the activation energy. All right, this is called the activation energy, and you have to provide this activation energy to this reactant, okay, these reactants, so that they can go and form a product. If this activation energy is not given, the reactant will never come from reactant to product side. It will never come. If this activation energy is not there, it will, the energy, if we, let's say that in a fraction of second, like a 0th second, the energy of the both product is here. 0.001 second, we've measured the energy, we will find the energy is here. 0.002 second, we will find the energy is here. 0.003 second, we will find the energy. So in this way, with time and energy, if we plot it like Excel, make the Excel figure, we'll see that the energy is increasing at the beginning and then it is decreasing. All right, so the energy is increasing is due to it needs to cross the barrier. Okay, this activation energy barrier, it has to cross. What is this activation energy? This is the minimum hurdle. Once again I'm telling, this is the hurdle that it must overcome so the reaction will cross over to the product side. This is activation energy. Okay, so question number 2, another thing. Do you have any questions so far? Please, do you have any question? Anyone? No. Okay, so question number 2, we are going a hand warmer purchased by campers, those who are in the cold countries where they go for skiing or this type of sports. So they need, this is very cold there, they need a hand warmer, and what the pack look like, it is on after 3 or 4 slide, it is given there. You can have a look, or I will go there soon. So the question says that a hand warmer were purchased by some people, and due to this component or reactant in the hand warmer, is the chemical reaction goes on inside, that iron and oxygen reacts together, and it produces, it becomes ferric oxide. All right, so it becomes ferric oxide, and that is how it produces a lot of heat. It is 823 kilojoule. It is much more than 300. All right, it's much more than the food warmer. It's much higher because it is in, you are in the snow. You are in the snow, and your hand or legs, feet becoming cold. So you need a much more higher heat somehow, to extent. I don't know, I've never experienced it, but okay. So the heat is produced is 823 kilojoule of heat is this reaction. So can anybody tell me whether it is exothermic or endothermic? Gabriel, yeah, exothermic, because thank you. So, I mean, makes that you are listening. I hope that all of you are listening. So this is an exothermic reaction because it is first it is negative sign, and also it says that it will be a hand warmer, so it will produce heat. Now the main question, this is the description of the question. The main question is here that a bag contains 15 grams of iron that reacts completely, all right? There is no leftover of the iron. All this 15 grams of iron will react. So the first question is, draw the level of a diagram to show the energy changes that occur during the course of the reaction, an energy profile diagram. I mean, in the question, it can be simply says that, okay, draw an energy profile diagram, or sometimes it can be in very broad and wide way to say that, okay, draw and label the diagram to show the energy changes, blah, 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 blah thing. But you guys know that it is the energy profile diagram actually. And question number B is calculate the energy released by the hand warmer, and C, suggest why salt is included in the content of the bag. So first of all, we have to draw an energy barrier, that how this thing is going, how it is happening. We will draw it later. Question number B is something that it is, what do you call it, makes us to feel interested, that how much energy will be released. It already says 823, right? Then why the question is asking how much of the energy will be released? Have to calculate. Why? Well, there is a trick here, because it says 15 grams of iron. Okay, so you have to read the question very carefully. It's 15 grams, but here it says that 4 moles of iron will produce 800. 15 grams means how many moles? Right, that is the thing that we need to find out. So this is the energy profile. Since it is exothermic, the product energy or enthalpy will be lower than the reactant. Once again, please listen. This since it's exothermic, the product energy level will be less than the reactant. So reactant energy is here, and product energy is here, somewhere here. If we draw a straight line, something I cannot draw, but if you use a ruler and draw a straight line, you will find somewhere here. So this is the difference between them, all right? And from here to the top that it has to cross the barrier. This is the activation energy. This is the activation energy. And this is the enthalpy of the reaction that the reaction is producing. So this is the energy profile. But if you just draw like, this, you will not get any mark. Okay, be careful. If you just draw like this, like you draw energy this side, the reaction progress this side, and then from here you start, okay, done. No, you have to label where is what. This is reactant, this is the activation energy, this is the product. From here to here, what is the total energy, this is the activation energy, this is the exothermic reaction, blah blah thing. So you have to label as well, not just draw. And as I said, that question number B says that how much energy it will be produced. Only 15 gram of iron was used. So 15 gram means 2.686 mole, right? How do you find it? Just divide gram per mole. We discussed this in second or third lecture. So how to find the number of moles, right? So if you have any shaky start, please go back and then listen to the recorded session already, or if you have any specific question, you can email me. So this is how we find the number of moles, that gram per molecular mass, that is gram per mole. So this gram and gram cancelled over and then cancelled out, and this mole is here. From denominator comes to numerator. So the number of moles. So 15 gram of iron is 0.2686 moles. And sorry. And since the question is saying that how much of the energy will be produced, from here we see that 4 moles of iron produces 823 mole. 823 kilojoule of this energy. So 0.26 to how much it will, it is quite straightforward way we can, and then we find is 55.3 kilojoule per mole. All right. Okay. So this is how the hand warmer looks like. I never touched it, just saw it on the photo. So probably they just shake it and hold it on their hand, probably. So question number 3, C, actually, why the salt is used? Because we know salt, let's say the sodium chloride. Sodium chloride is also a salt, right? Sodium chloride, potassium chloride, sodium carbonate, all those salts. So sodium and chloride is a good electrolyte because they can divide into ions upon contact with water or aqueous medium. They will be separated in ion, and we know that ions, they are good in carrying charge because they themselves are charged, right? Sodium is positively charged, chloride is negatively charged, so they are there will be charge, so they carry the charge. That is why water is a very poor electrolyte, but when we put a little bit of salt in the water becomes heavily conductive. But do not touch, and in the water, I mean at home, don't try this, but just believe it, it is true. Okay, so this is why the salt is used to conduct the heat, the charge faster and more evenly, more efficiently. That is why electrolyte is used. Question number 3, that octane, this is probably the petrol RON 97 that we use for your car. Not all car needs it, but some people, yeah, those who use the octane. We have petrol, petrol actually a mixture of many things. Octane is more purified, so 97% of this is octane. It's called octane. So in octane, the major component is a major component of petrol. All right. So petrol also has octane. And it says that the complete combustion, why do we use petrol in the car? Because it can produce a lot of heat, right? It produces a lot of heat and a lot of gas as well, so that the piston in our car can move far. I mean, we can move the pistons so that our car can move, our vehicle can move. So this octane is become combustion in a following equation, that octane and oxygen produces carbon dioxide and water, of course in gaseous form, it is not in liquid form. So water vapor will be produced and a lot of heat, 5054 kilojoule. Goodness, that is too much of the heat it will be produced. All right, from 1 mole, all is, you need 1 mole of octane to produce this number of kilojoule of heat from there. And this question is saying that calculate the energy released when 1.8 liter of petrol undergoes combustion. Okay, given that the density of octane is 7.703 gram per milliliter. One thing, if you are environmentally concerned, have you noticed that 1 mole of octane is reacting with 12.5 moles of oxygen? Imagine how many cars on the road and how much oxygen it needs to burn, right, every day. All right, so okay, we come back to our problem that it says that 1.8 liters of petrol undergoes combustion. How much of the energy we can find from this 1.8 liters of petrol? What is the strategy? What will be our strategy? Of course, 1.8 liter, I already have told you, right, that 1 mole produces 5054 kilojoule. So 1.8 liters mean how many moles of octane, isn't it? How do we find the moles of octane? We have to divide gram over mass, the mass of octane over the molecular mass. So that will be M, just like the previous slide, M over molecular mass, MR. But to find the mass of octane, because this is in volume, liters, right? So 1.8 liters, we have to convert to mass first. How do we how do we convert this 1.8 liters to mass first? Because here we know the density, right? Density is 0.703 gram per milliliter. So 1 milliliter will have only 0.703 gram. So that we convert either this one to liter, gram per liter, or kg per liter, or this 1.8 liters to milliliter. And I think 1.8 milliliters to milliliter is easier. Just multiply by 1000 and then I will find 1.8 milliliter is actually 1800 milliliter. And we multiply with this density, because rho, this is not P, this is rho, is equals m over v, that is density is mass over volume. From there we find the mass, and the 1.8 liter of octane has a mass of 1.26 1.2 kg, or yeah, something like that, 1.26 kg of that. So in 1.26 kg, or this gram, how many moles of octane is there? First, we have to find the mass, molecular mass of octane. How do we find it? Because it is C8, right? C8 and Okay, C8 and H18. That means 8 carbon is here and 18 hydrogen are there. So 8 carbon, from there we can find out the mass is 8 times 1 carbon is 12.01, right? 12.01 plus 18 hydrogen is 18 times 1. 1 hydrogen is 1, the mass. So from there we find that mass of octane is 114.23. So we divide the gram or mass of the octane by this molar mass, we find 11.08 mole. So since 1 mole produces 5054, 11.08 mole will produce quite huge number of energy it will produce, isn't it? And also we see that 11 mole will need how many moles of oxygen to burn? All right, you can calculate that at your own pace. You can try to find out that just to 1.8 liter in a normal car like a 1300 cc 1.3 liter engine car, 1.8 liter will give you a mileage of like 30 kilometers, around 25 kilometers maybe. So in that 20 kilometer, 25 kilometer, how much oxygen you burn, you can calculate from that. Just a thought, something to give you to your thought. Okay, so now we are going to the activation energy. We use this petrol or gasoline or octane or the methane gas that we use for our cooking, right? LPG gas. Those gas in our home, even in the cylinder, and we are okay with that. We do not feel much bothered, and the gas is very much combustible, but it does not readily become fire. We need to have a spark, either by a match box or from a gas lighter or from other means. You have to have a spark. If there is a spark, then only the gas starts to burn, right? So why is it so? And if there is no spark, then what is actually happening? That there is a spark and it is becoming a burning, it starts to burn. This thing actually is here, this is oxygen, right? And we have the petrol or octane or whatever, let's say it's petrol, octane, and we have petrol plus oxygen is here, and there are a lot of petrol and oxygen. Petrol actually hydrocarbons, so this is the hydrocarbon octane, this is the formula of it, and this is the structure of octane. All right, this is the structure of the octane. So it is a hydrocarbon. Hydrocarbon means carbon. We will see. We will learn more about next. When we go for organic chemistry. So this is also hydrocarbon, and they are together, but they are not having anything. Even sometimes you feel that when you open the stove at home, sometimes it says that check your kitchen. If there is a gas, you feel the smell of the gas, do not light, do not ignite anything, right? Because that is dangerous. But just open the window, the gas will go out. All right. So this is in the air inside the kitchen, or there is gas and there is oxygen as well. Oxygen means from the air there are oxygen, but it does not burn. It doesn't start burning. Why? Because this is the thing, the activation energy. they do not have to cross over this activation energy. When this activation energy, they will go up in here. When the energy is up in here, they start to react to each other. But until here, just before here, they will be together, but they will not do anything. They will be there, they will be colliding still, but they will not go to the product until this, till it reaches this point. When it reaches this point, they start to form bonding. Okay, they start to form bonding and then they produce the product. So this is the activation energy. The activation energy is the spark. The spark gives activation energy to, let's say, 1 or 2 molecule, and then 1 or 2 molecules start to burn, and it provides the activation energy to others, and then there is a sudden blast, you see. So that is the thing, the activation energy, that it gives the to give the energy to produce, to break the bond and produce a new bond, and for the reaction that can produce. So this is what activation energy is. And now we are moving to the reaction kinetics, or reaction rate of the reaction, or what are the things that will affect the reaction rate. Before I move to this thing, I want to ask that if you have any question. Do you have any question, anyone? Is the rusting of iron a reaction? Yes, the iron rusting, yes, the ferric oxide, it produces, yes, this is the same thing that is called the rusting. Okay, so any other question you have? Anyone has? No. Okay, so now we are moving to the collision theory and reaction kinetics, that for reactions to occur, reactant must collide, right? You put A and B, this A and B, or just now we saw here from this slide that hydrocarbon, oxygen are there, CH, CH are there, and oxygen is also there, but they are not reacting. They are not reacting. Sorry, they are colliding each other. That means colliding means they are having the bump to each other. They are hitting each other. That there is a collision between them. All right. So there is collision is happening, and the collision is happening, and then due to this collision between, because they are having collision between them, so due to this collision there should be an energy jump in energy, right? So like one example I think it's a funny example, but I cannot find anything else better. So when you hit, we clap together, right? Like this, when we clap together, we feel our palms become a bit hot. We feel a little bit hot, our palms. If you clap a lot, that means when there is collision between two surface or two components, there will be some energy. There will be produced some energy, and that energy, not every reaction needs this spark, right? Not every reaction needs this, like the gas or octane or petrol. It does not need a match to strike or a lighter to strike, right? To make a what do you call it, spark. Some of the reaction happens when we mix together, they will collide and they will provide that energy. They themselves will provide bring out the energy, okay? So that is how they will cross over the energy barrier or the activation energy barrier. They will overcome those activation energy barrier. And that rate of the reaction, that is why the rate of the reaction depends on how successful or how much of the collision is happening. inside the molecular. I mean, you think in the molecular level, like some atoms are very lazy. They are colliding once in a while, and some atoms are very fast. They are colliding each other very, very frequently. So those who are colliding very frequently, they will have higher energy. The activation energy will be, much fast. They will overcome this activation energy barrier. So if any reaction has a very high activation energy, like very, very high, that of course, if you have a very high hill or mountain to cross over, we will take a long time to cross. But if we have a hurdle, a shorter, what do you call it, not that high, or what is the opposite term for high? Low. If we have a lower mountain to cross, then we can cross faster. So that's the same thing. If the high activation energy for that reaction to occur, the reaction will be slow. For this question number 4, I should go, okay. For this question number 4, it says that which of this following graph most likely represent the slowest forward energy? As I said, we just discussed that here we have activation energy of about, it starts 70 to 150 maybe, right? So it's 50 kilojoule of activation energy. It is 100 kilojoule activation energy, 75. So since it is higher, not just by look, but the value is much higher, 100 kilojoule. That is much higher than any of those, so that the reaction will be slow. So one thing that we learned, that activation energy is the factor that can slow down one reaction, or actually it is one of the barrier, one of the factor that will stop the reaction to occur faster or slower. That is one. But there are 4 considerations actually to make for a reaction to fast or go slow. One is the surface area. All right. So what is surface area? Right. So most of you are from watching it from the computer screen. Some of you maybe from mobile screen, I do not know. So whatever the screen is, you know the screen surface, right? The surface of the screen we know, because the surface of the screen is the length and height. That if we multiply, we will find the surface area. Now, I'm giving another example is, if we break that mobile down, or mobile or the laptop, our screen, is break it apart, then what will happen is, I will have 2 surfaces from the same screen, isn't it? The front and back. The back surface that I cannot see now, or my PC screen, the back of the surface I cannot see now. I can only see the front surface, that is where I can see my slides. But if I break it, I will see the front surface and the back surface as well. So that means my surface area increases in this way. So if anything, like if a big ball, solid sphere, is broken to pieces, what will happen is its surface area will increase. So if we break it down, or if we make it very small particle, the surface area will increase. Okay, so surface area is important, and if the surface area increases, right, that means more collision will happen. Since the surface area more, the more particle can get bombarded on the surface to each other. That means more energy can be produced, and more energy produced, that means it will be easier for them to cross over the barrier, activation energy, and produce products, so that the reaction rate will increase. Second, increase the concentration of reactant, pressure of the gases. Concentration, if the concentration increases, that means concentration means mass over volume, right? Mass over volume. Let's say for here I have only 3, 4, right? Particles inside. So they will have less friction. There will have less possibility of having more friction. But if I have 100 in it, there will be more friction, more frequently, more vigorously, isn't it? So that is what it says, that if the concentration increases, there will be more chances of occurring this collision or friction, and that is how the reaction rate will increase. For a gas, let's say this is the piston, and the gas I am increasing, I am pressurizing, that means I'm pushing the piston down. This is down, I'm pushing this piston down, so that what I'm doing is I started from here, I am going to this position. I'm taking the piston to this, so that all the gas has been, what was here, all those gas here, it has been compressed in heat. All right. If it is compressed, that means even more concentration is happening, right? So that it will react more in that case. Increase the temperature. If I increase the temperature, that will also increase the friction. Like here, these components are moving faster, right? The components are moving from, let's say here, this one is moving to this side, this is moving to this side. So this way the components are moving, or sorry, the molecules or atoms are moving from here to there and colliding to each other. So if I increase the temperature, what will happen is they will start moving more faster, because the temperature, when the temperature increases, they start to shake more, or not shake actually, how to say that? They start to vibrate, they start to vibrate more. So when they have more vibration, they will start to collide more faster each other. And then the reaction is going to occur faster. But sometimes we need to remove the temperature so that the more reactant will be produced, product will be produced, and the reaction rate will faster. We will come later on there. Adding a catalyst. What is a catalyst? All right, this is all those things. Increase the surface of the solid. Once again, I should come here actually. Okay, increase the surface of the solids by breaking it down or making a very fine powder, so that from here, example, in the childhood, we tried to do this, right? We put in our tongue and it becomes fizzing, so much bubble comes out from it, and we see that it was fun in childhood. For the fireworks, that this type of fireworks that we see during our festival or this season, this is the more fine the particles or the reactants are made, aluminium, sulfur, and all those manganese, chromium sometimes are used, and all those chemicals that are used, that the better the surface powder form, the better the reaction, and the longer it will burn for them. Okay, sorry, the better the reaction and more spontaneously or more faster the reaction will occur. If the particles are larger or bigger, it will burn slowly, and sometimes it will not even burn completely. So particle size is important in that way. Concentration, that I just said that if we increase the concentration of a solution, it will increase the frequency of collision of the particles, and they will frequently collide each other. And increase the pressure of the gas is also the thing that if we just like the piston, we push it down the piston, then the gas will be pressurized and they will form more frequently. Temperature. Okay, so as the temperature increases, the average kinetic energy of the particle increases, that the movement or the frequency of the vibration of the particles will increase, and thus the kinetic force, kinetic energy of the particle will increase more. The frequency of the collision, since the kinetic energy or vibration will increase, the collision will also increase, right? So this is how the temperature helps to increase the rate of the reaction. Maxwell-Boltzmann, that is the distribution actually, this is the distribution of how particle can be distributed in a system or for some kind of a practical, for kind of a theoretical work, how the particles should be distributed. Maxwell-Boltzmann distribution actually gives us the idea of how, but for our case, we see that 20 degree and 30 degrees centigrade, all right? For 20 degree and 30 degrees centigrade, there will be the distribution of the particles in these two ways we can see. In 30 degree, the red color, all right, it goes in this way, and at the end it is going this way, but for 20 degrees it is here. So number of particles in 20 degrees, it shows that it is more particles are reacting at 20 degrees centigrade, but for 30 degrees it shows that with the temperature being high, these particles move faster to the product side, okay, because they have more higher kinetic energy. So they react, like they bump, and then they cross over the energy barrier. So they had to bump, or they had to collide less than 20 degrees centigrade, because when they are bumping at 30 degrees, since they have more kinetic energy, one bump, let's say, I'm giving an example. Let's say one bump is like 2 bump in 20 degrees, or one collision is like 2 bump in 20 degrees. That is why they have more higher energy and more particles. Number of particles is less here, but more in here. This is product. EA is after the activation energy, right? So EA, this is the activation energy. So they are crossing, more particles are crossing the activation energy. And this is underneath this graph. This is the volume of the particles. So more particles for 30 degree is going to the product side, but for 20 degrees centigrade, less particles are going. This is much less. The area under this 20 degree is much less than 30 degree. 30 degree area is more. So more particle in 30 degree is going for the reaction, I mean product side. Okay, so this is what I was just talking. Now we are going for the catalyst. Catalyst is a foreign thing, and it is used to increase the rate of the reaction. But the interesting thing for the catalyst is it does not take part in the reaction. Okay, it will never take part in the reaction. It will just facilitate the reaction to happen faster, and then it will be unchanged. It will never be consumed in the reaction. If it is consumed in the reaction, it is not a catalyst, it is a reactant. Okay, so this is the difference between catalyst and a reactant, that reactant will be consumed in the reaction, catalyst will never be consumed, it will be as it is. And it can be used for other similar reaction without any modification. So that is what a catalyst is. And how does it work? They provide an alternative path. They provide a cheat code for the reaction to occur, all right? So that is what a catalyst do. And almost all the reactions nowadays in industrial level, some kind of catalyst are used for all the reaction, because it reduces the time and energy and effort and manpower, and it produces the, I mean, it increases the profit for the industry. So catalyst is a very important thing now in the catalyst is a very subject of a very deep research for long time actually. Now, even now, catalyst is a very interesting research. There are very types of catalyst, can be homogeneous and heterogeneous. Homogeneous reaction catalyst is the same state as for the reactant and product. Okay, like we have a reactant in gaseous and both are in gas form or both are in liquid form. Like A and B, we have reactant side, right? A plus B, which is producing C plus D, which is producing C plus D, let's say. Just an example. So let's say A and B both are solid or both are liquid. So if it is solid, yes, right, A and B both are solid. So if I use a catalyst which is solid as well, like a metal, some kind of metal which is a solid, then we can call it a homogeneous catalyst, because the catalyst is in the same phase or same state, like solid state. Or if it is in liquid, both of them are liquid, L. Okay, both of them are liquid, and I am using some liquid catalyst like what do you call it? Hydrogen peroxide, or if I am using any nitric acid or sulfuric acid, whatever, this is in liquid form. If I use, that will also be a homogeneous. That means the catalyst is in same state or same phase as of this reactant. But if the catalyst is in different state, right? If the catalyst is in a different state, then it will be heterogeneous catalyst. Like both of them are liquid, but the catalyst is solid, or both of them are solid, catalyst is liquid, or one of them is solid, one of them is liquid, and the catalyst is liquid or solid. So it will also be heterogeneous as well. How do the catalysts work? And this reaction that you are seeing in front of your eyes, it revolutionized the whole chemical industry like 100 years ago. It's such a simple reaction, but the chemistry just took a very big leap ahead to the modern chemistry today from this reaction, from this Haber process. Actually, this reaction, I mean, this occurs for a very, very long time, thousands of years it occurs. Nitrogen and hydrogen, they react together, and ammonia gas is produced, all right? This ammonia is very important for agricultural product, because the urea or some other agricultural product, urea mainly, is used, this ammonia is used to produce urea, that is a very good fertilizer. And ever since, just for your information, ever since we knew how to produce this urea, all right, or ammonia, I mean, conveniently, faster, effortlessly, since then, the human civilization saw less famine. That means we can produce more agricultural crops, we can grow more food, and the food price become cheaper, much more cheaper. But there is a grim or bad side about this ammonia production. This Haber process I forgot the numbers. He's something Hebert, this guy, the scientist actually, who won the Nobel Prize in chemistry in 1930, I think, something like that. This same process was used to produce the weapon for the First World War, I think, or Second World War. I think First World War. So, no, Hebert process is 1910 or 1915, something like that. So, this process also include the production of weapon, mass. So people go to the war, they will become more invincible. They thought they were invincible. They started to do more war, and this because of this ammonia production, because this ammonia also is needed for explosive. Okay. So how does that catalyst works? All right. The catalyst, that ammonia, nitrogen and hydrogen is there in the environment. In the environment, actually, we have, do you know, can anybody tell me that how much of, why cannot I see? How much, can anybody tell me how much of nitrogen, of, how much of nitrogen in the environment, in the air? Can anybody tell me? How much nitrogen do we have in our environment, in our air? Bernie 70, yes, good, thank you. How much hydrogen do you have? Okay, how much oxygen do you have? Okay. Oh, Bernice is very precise, 16.23. No, yeah, around that actually, 20, 22%, 75, 78% of nitrogen, and 1% of hydrogen, and there are trace amount of others like argon, helium, blah, blah things in the environment. So my question is, if there is 78% or 80% almost is nitrogen and 1% of hydrogen, why they are not producing ammonia? What's the problem? Isn't it? They should be producing ammonia. Gabriel, yeah, it's good, 78-21, yeah. And then another 1% and the trace amount is gases. Because they cannot pass over this activation energy barrier normally, all right? So they need something, or they need more in a force or support to cross over this activation energy. I'm going there, but first let me address this question from Bernice. So the higher temperature, the lesser the collision of the particle? No. The higher the temperature, the higher or more frequent collision happens in the particles. Okay? And cloud, this, they say that the collision, the particle increase, I guess. Yes, thank you. All right. Okay, so I'm going to this lecture slide again. So what happens is nitrogen and hydrogen, then the iron, a little bit of iron, a very small piece of iron, they give this surface, this is the top surface. If we see through the very strong microscope, maybe, I mean, very electromagnetic microscope, we will see that the very surface of the iron is like that, and nitrogen and hydrogen actually can sit together, all right? They can sit together, have some time, and then they react to produce ammonia. And in this way, that is much, very fast. All right. So this is how catalyst works. It gives a cheat code them to do the reaction by providing it another pathway. The another pathway has less activation energy, or requires less activation energy. Okay, so if we see that diagram for this, if we see the diagram for this the energy diagram for nitrogen and hydrogen and ammonia production, we see that here originally it should go in this way. Okay, this higher activation energy, it has to cross over to go to the product. But when I use the catalyst, that is iron, it will cross over only this. Why? Because at a time on the surface, only few particles, particles of nitrogen, hydrogen will sit, right? Because it is a small amount of iron, piece of iron, and it will only allow only few amount of hydrogen, nitrogen to sit together. When they sit together, they come close to each other. So they come close to each other, and then only they have better understanding, and then they form a product. So that is how they produce this catalyst gives a different or alternative pathway to the reaction. So how catalyst and uncatalyzed pathway. So this is what exactly I was talking about. You can go through later on. This is with no catalyst. That means more particles are actually frequently they are colliding each other, but they cannot go over the energy barrier. But with the catalyst, these more particles can actually go to the product side. That is cross over the energy barrier and go to the product side. Which energy level will change when the catalyst is added? Of course, 2 and 3 only, because catalyst will give you this, what do you call it, alternate pathway, so that it will reduce this activation energy. And another thing is the reverse reaction will also be possible. All right, just like this, if it is a reversible reaction, all right, which ammonia is, since this iron is giving a pathway or a space for them to produce the product, this product will also can be broken down to the reactant, because this iron is neutral. It does not take side to anyone. It will give space to both of them, nitrogen and hydrogen producing the ammonia. Ammonia will also sit on it and then break apart, produce nitrogen and hydrogen. So that is why the reverse reaction is also possible for it. But the enthalpy of the reaction will not change, right, for using this catalyst. So the summary of this today is when the product is produced here, this is the exothermic reaction, when the product is less, the energy of the product is less than the reactant, and it is endothermic when the product is higher than the reactant. I am not done yet, just another thing, another menti.com we have, I produced today. So let me go there. Go to the Menti so that you can do it faster. I give you the code now. After that, and if you have any question, prepare the question. After this Menti question, I will take the question. Why cannot? Go to menti.com, then 6846 77 wait, 77737. So go please and then try this one. And you have 1 minute to do this. Okay, so what happened to others? Only 26 for both the mentee. What happened to the, I can see 33, 34 students are here, but only 26 students. Okay, but anyway, I cannot force you to do that. It's up to you. All right, so the thing is, their reaction is faster when there are more reactant. The more reactant does not mean the concentration of the reaction is higher. Okay, doesn't mean that the concentration of the reaction is higher. So it is cannot be correct. The higher the temperature, okay. So the higher the temperature is means that the reactant will, the kinetic energy is more, isn't it? The kinetic energy more, they will collide each other and then bump each other. That means kinetic energy is high. But there is lower energy hurdle barrier. If this one is more correct, because if the lower the energy hurdle barrier, that means the activation energy is low, then the reaction will be much faster. Even before you need to produce, give any temperature, the energy, the reaction will go to the product. Okay, so this there is lower in, if the energy hurdle barrier is low, that is much better in that way. It will much faster, it will facilitate much. Okay. So, oh, I got it correct this time. Yes, yes. You see that there is the thing that the satisfaction you get by doing it correct, but those who are not 100% correct this time, they also learn, right, by making some mistake. So we learn it by making mistake. We cannot learn or we cannot make it right at the very first time. That is the thing that we should learn. No, that's why I say that, okay, you try, you sit together, talk in the group. That's the best way you will learn, by making mistake. Anyway, yeah. So, Gabriel, sir, what is the format of the midterm will look like? Megan, I'm coming to you later, but Brandon say, is it an online test or paper test? Gabriel, what do you mean by the format? What section? I'm telling you that from 1 to 6, all the lecture and tutorial from 1 to 6 week will be included. Brian, I feel like you do not look at the announcement at all. I already said that in the announcement that MCQ plus the essay type question, okay? Like how many MCQ question and paper 2? Okay, I think I'm missing the thread. Let me go through. Like how many MCQ question and paper 2? What does it mean? MCQ question, there will be around 15, 16 MCQ question, okay? And paper 2, oh, how many questions will be there? I haven't set the question yet. That's what I say, that I will come on Monday, next Monday, for 1 hour to talk all about it. And the time and duration, somebody asked me the time and duration. The time and duration will also be posted next week. Time, you already know, there's 2:30, right? On Friday, 2:30. But the duration, whether it will be 2 hours or 2 or 30 minutes, it will be confirmed next week. And okay, I'm missing it. I got this correct mistake. Megan, sir, if I'm not mistaken, the announcement did not include the time and duration. Okay, time already said on Friday 20. When is that? It will be on 23rd, Friday, 2:30. But duration, I remember the duration I did not put. But duration I will put on once I become confirmed of the question. About the question, then only I put the duration. So don't worry about the duration, because you know that you have the test on 2:30 Friday, 23rd. Isn't it MCQ style, Brian? Yes, it is MCQ plus essay type. MCQ we have to do online, and essay type you do it on paper and then post it or send it or submit it through Canvas, just like you do for your lab as a PDF. Brian, I mean no to reply GAB, not to you, sir. Okay. Sir, for the project, the presentation, is it now changed to pre-recorded? No. Who said to you that it is pre-recorded? It is not. It will be live. Bernice, the presentation will be live, okay? We'll have 2-hour session. I will book a session. I will let you know on week 9. But since everybody is here, let me just announce it. It will be on week 9. That means on 11th of November, all right? But in your announcement, it is written pre-recorded. Is it? Did I say pre-recorded? No, it will be live, actually, it will be right. Okay, so it will be on 11th November, 2 p.m. 11th November, 2 p.m. I will announce it. 11th November, 2 p.m. to 4 p.m. Project presentation. Okay, 2 p.m. to 4 p.m. 11th November project presentation. There are 20, 30, 31, 32, 33, 34 students here, and I'm guessing that everybody is listening. So 11th November, 2 to 4 p.m. project presentation. I am announcing it 1 month earlier. So it is a lot, I mean, much advanced, I'm telling you. All right. So, oh, hold on. 11th November is week. Sorry. 11th November is week 10. It should be 4th November. 4th November. How do I delete it? 4th November 2020 Wednesday. Wednesday 2 to 4 p.m. Submission and presentation. Okay, so once again, project presentation submission is on 4th of November, 4th of November, Wednesday, 2 p.m. to 4 p.m. Megan, no, you can submit it later. That was the tentative date I put at the beginning, but now this is the confirmed date is 4 November, okay? All right, so is there any other question anyone has? If not, then I will see you tomorrow morning for the lab session, and also I will discuss about the project, those who are interested.